Why waste time in commute and spend lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
Hello everyone, welcome to this video. In this video, we are going to talk about alternating current. So in the previous lectures, we studied what is alternating current and how it is different from direct current. So direct current is a current that is constant throughout the time. So the current which is not changing is called direct current. But alternating current is time dependent. So when I say time dependent, with respect to time, the current is going to keep changing. So how it changes, we already talked about in the previous lectures. And also we studied what happens when you apply an alternating voltage to a circuit with a resistor. So we looked at the current, we applied alternating voltage to a resistor, and we looked at how the current is. So when there is a resistor, just a resistor in the circuit, the current and the voltage are in phase. So when I say in phase, the angle, that is omega t, is constant for both of them. But is it the same thing with a capacitor, or when you add more element like inductance, capacitor and resistor in the same circuit, how the value of current and voltage is going to change? So that's what we are going to study in this lecture. So in this lecture, we will just talk about what happens in a circuit which has a capacitor when you apply an AC voltage, and similarly what happens to a circuit when you apply AC voltage, when the circuit consists of an LCR circuit. LCR means inductance, capacitance and resistance. So when all three of these things are combined, what happens when you apply an alternating voltage to the circuit? Let's begin. So the first thing is, what happens when you apply an AC voltage to a capacitor? So we all know what is a capacitor. A capacitor normally has two parallel plates where when you apply an voltage, the capacitor charges, and when you remove the voltage and then connect both ends, then it discharges. So the plates of the capacitor can accommodate some amount of a charge Q when you charge the capacitor, and then when you remove the power source and then connect the ends of the capacitor, then it discharges. So we know what is a capacitor and how it functions. So what happens when you have a capacitor connected to a voltage source in a DC circuit? Remember, DC circuit means it has DC voltage which is a constant voltage. So when you switch on the voltage, it goes from 0 to a constant value, and that's it. It won't change after that. So what happens? Current will flow for a short time required to charge the capacitor. Once the capacitor is charged, then it cannot hold any more of the charge. So the current stops. So as charge accumulates on the capacitor plates, the voltage across them is going to increase, opposing the current. Now at some point, the current is going to stop. That is the point when the capacitor is fully charged, the current in the circuit falls to zero. So this is the case when you connect a capacitor to a DC voltage. But what happens when you connect a capacitor to an AC voltage? So when the capacitor is connected to an AC source, as shown in this picture, there is an AC source here and there is a capacitor here, and we have a circuit like this. So when you connect to this capacitor to an AC source, it limits or regulates the current, but it does not completely prevent the flow of charge like in the case of DC current. So how it happens? We know what is an alternating voltage. It will just look like a sine wave. So some of them will be positive and some negative half cycle will be there, but it is not constant like the DC current. The capacitor is alternatively charged and discharged as the current reverses each half cycle. So when we have a positive half cycle in this voltage, what does it mean? It means the voltage here is positive. So this will be positive, this will be negative. When the current reverses its direction, or when the voltage reverses its direction, it means then the polarity of where the positive and negative are connected will also change. So then the capacitor will start discharging. So this cycle keeps happening. Okay, let's look at it mathematically. So if Q is the charge on the capacitor at any particular time t. So why are we considering the time here? Because it's an alternating current. So the voltage is time dependent. When the voltage is time dependent, the current is also time dependent. So the charge on the capacitor. The charge on the capacitor is not like constant anymore. It's going to be dependent on time. So if it is dependent on time, what is the instantaneous voltage? Instantaneous means at this particular time, what is the voltage? At any particular time, voltage across the capacitor can be given by Q by C. So this we already studied when we studied the capacitors. So if you look at that circuit and look at Kirchhoff's loop law, the sum of all the voltages has to be zero. So if there are only two elements in the circuit, one is voltage source, which is Vm sin omega t, and another one is the capacitor. So the voltage across the capacitor is Q by C. So both of these things have to be equal because Kirchhoff's loop law says that in a closed loop, the sum of all the voltages has to be zero. So these two elements have to be equal to each other. Otherwise, it will not solve this loop rule. It will not follow the loop rule. So this is the case. So Vm sin omega t should be equal to Q by C. So we have a relation that has Q by C, which is equal to Vm sin omega t. And what is Q? Q is the charge. So how do we find current from charge? I equal to dq by dt. So let's take Q from this equation. Let's differentiate that. So I equal to d by dt into Vm sin omega t multiplied by C. C we are bringing to the left hand side. Then if you just differentiate this with respect to time, what you get omega c Vm into cos omega t. So this is nothing but I. What is I? Current in the circuit at a particular instant of time. So that's why it contains a omega t here, because it is a time dependent current. It's not a constant current. But what is constant here? This element here, omega c Vm, is the constant here, which is nothing but the magnitude of the current, or we can say amplitude of the current. Okay, so let's look at this. So now cos omega t can be written as sin omega t plus pi by 2, because we know cos theta equal to sin theta plus pi by 2. So if we do this and then take all of this element omega c and Vm and substitute it by Im. What is Im? Im is the amplitude of this current. So if you have a sine wave, then you will have an amplitude and then you will have a phase. The phase is nothing but omega t, the amplitude is this. So the amplitude of current is given by Im equal to omega c Vm. So if you substitute both of these quantities into this equation, you get I equal to Im sine omega t plus pi by 2. So what is this value? This is the current in the circuit at a particular instant of time. Okay. So now by rearranging this equation, this is nothing but the amplitude. By rearranging this equation, you can get Im equal to Vm divided by 1 by omega c. It looks like Ohm's law. What is Ohm's law? I equal to V by R. So in the left hand side you have I, in the right hand side you have V divided by, instead of R you have something else here. What do you have? 1 by omega into C, which is equivalent to a resistor here, but it contains the term capacitance and omega, that is the frequency of the applied voltage. So this whole term we can take as, okay, so when we compare this with Im equal to Vm by R, instead of R we have 1 by omega C, which can be denoted as capacitive reactance. So this is the resistance that a capacitor is giving to the circuit because of this alternating voltage. So that equivalent resistance is called as capacitive reactance, which is nothing but Xc equal to 1 by omega C. So now if you substitute this in the amplitude of the current, it becomes Im equal to Vm by Xc. So it just means that if Vm is your applied voltage's amplitude, and you have a capacitor with a capacitance C in the circuit, and you have a frequency of omega for the applied voltage, then the value of current or the amplitude of current is going to be Vm by Xc. Xc is nothing but 1 by omega C. Okay, so now let's look at this value or this element called capacitive reactance little bit more closely. So what is capacitive reactance? We talked about it and we thought that it's equivalent to a resistor. So it has to have the units of resistance, which is ohm. So it has the dimension of resistance, and the unit is ohm. So the capacitive reactance, what is the role that this capacitive reactance plays in the circuit? So the capacitive reactance limits the amplitude of the current. As you can see, this value is in the denominator. So the current is going to be limited by this value, because if this value increases, the current is going to decrease. So it limits the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit, because in a purely resistive circuit, I equal to V by R. So the R is in the denominator, which limits the value of the current in a circuit. Similarly, if you don't have any resistance in the circuit, but you have only a capacitance, and you apply a voltage source that has a frequency of omega, alternating voltage which has a frequency of omega, then this value Xc is going to act as a resistance for that particular circuit. So it is inversely proportional to the frequency and the capacitance. So it is 1 by omega C. Now let's look at this value of current here a little bit more closely and see how it relates with the voltage. So voltage, when I say voltage, I mean the applied voltage. So here the current is pi by 2 ahead of the applied voltage. Let's look at the phasor diagram. We talked about what is a phasor diagram in the previous lectures. So the phasor diagram has two vectors here. This vector represents I, this vector represents V, the voltage, and Vm sine omega t is the value of this voltage. V equal to Vm sine omega t, Vm being the amplitude of the applied voltage. Similarly, Im being the amplitude of the applied current. So I equal to Im sine omega t plus pi by 2. Why there is a pi by 2? Because we derived it. There is a pi by 2 because we had cos omega t. So we substituted omega t plus pi by 2. So what does it mean? Here if you see V equal to Vm sine omega t, and here it is Im sine omega t plus pi by 2. So the current is pi by 2 ahead of the voltage. So the phase of the current, if you look at this diagram itself, this is omega t1, that is the phase phi, but the current is 90 degree ahead of this. Okay. So let's look at it here and see. So the voltage starts from 0 and goes like this, but the current starts from here. That means the rest of the current must be here. So the 0 of the current has to be here. So it starts 90 degree ahead of the voltage and it continues. That's how we get this kind of a diagram. Okay. So the phasor diagram at an instant of t1, here the current phasor I is pi by 2 ahead of the voltage phasor B as they rotate counterclockwise. Figure shows the variation of voltage and current with time. So this is the variation of voltage and current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. So the voltage maximum comes here, but the current maximum comes here itself in the 0. So it is pi by 2 ahead of the voltage. Now let's look at the power. What is power? Power equal to I multiplied by V. Power at a particular time, so instantaneous power will be PC equal to, since it's a capacitor circuit, I into V. So I is nothing but Im cos omega t and V is nothing but Vm sin omega t. So if you multiply these two, then you get Im Vm into cos omega t sin omega t, which is, we can substitute that sin 2 omega t by 2. So power of this particular circuit, which consists of a voltage, alternating voltage source and a capacitor, the power at any particular instant will be given as P equal to Im Vm by 2 into sin 2 omega t. So this is the instantaneous power. But how will you find out the average power? Let's look at the average power. So you take the average of this particular value. You can take these values outside and take the average of this. A sine wave has a positive half cycle and a negative half cycle. But if you take the average, it becomes 0. So the average power for this particular circuit is going to be 0 because the average of any sine wave is going to be 0. In the case of an inductor, the current lags the voltage by pi by 2, which we talked about already. But in the case of a capacitor, the current leads the voltage by pi by 2. So that's the difference between a capacitive circuit and an inductive circuit. So what we studied so far is we have a circuit with a capacitor with a capacitance value C, and we have a voltage source, alternating voltage source, and then we studied what will happen to the current, and we found out that the current leads the voltage by pi by 2, and then we figured out what will be the power, instantaneous power and the average power for this particular circuit. Okay, now we are going to look at what happens really inside the circuit when you apply the voltage. So let's look at the quarter cycle. So 1 by 4th when on the positive half cycle. So the current I flows as shown, and from the maximum at 0 reaches a 0 value at 1. The plate A is charged. So this A and B are the plates of the capacitor. First A is charged to positive value because now positive terminal of the battery is applied here and negative terminal is applied here. Now we are in the positive half cycle of the voltage. Now the plate A is charged to positive polarity while negative charge Q builds up in B, reaching a maximum at 1 until the current becomes 0. The voltage V equal to Q by C is in phase with Q and reaches maximum at 1. Current and voltage are both positive, so P equal to VCI is also positive. Now what is happening? P is positive. Why? Because current is in this direction and voltage is also in this direction. So both are in the positive direction. So P is also going to be positive. When P is positive, it means that energy is absorbed from the source during this quarter cycle as the capacitor is charged. Now the capacitor is getting charged in the first quarter cycle. So we are just taking 1 by 4th of the cycle and looking at it. Now let's look at the next quarter cycle, next 1 by 4th of the cycle. Now what happens? The current I reverses its direction. The accumulated charge is depleted. The current is discharged during this quarter cycle. The voltage gets reduced, but it is still positive because the voltage we have just talked about the first 1 by 4th of the voltage. The next 1 by 4th is going to be the voltage that is reducing but still positive, but the current is negative. So their product power is also going to be negative. Let's look at it from this picture. Okay, we are looking at the first quarter cycle here where the voltage is increasing, the current is decreasing, but both are positive. So power is also positive. Now, if you look at the next quarter cycle from pi by 2 to pi, the voltage is decreasing but positive. The current is decreasing but negative. Current is increasing in the negative direction. So when current is negative and voltage is positive, the power is supposed to be negative. So that's what we are looking at in the second in this half cycle. So the power is negative. When the power is negative, the energy absorbed during the first half cycle is returned now because the power was positive in that quarter cycle. Now it is returned to during this quarter cycle. Now let's look at the next quarter. So as I continues to flow from A to B, now I is going towards 0 and capacitor is charged to reverse polarity. The plate B acquires positive charges and A acquires negative charges. Both the current and voltage are negative in this quarter cycle. So then we have P is also positive. Again, now the capacitor absorbs energy. So remember, if the power is positive, the capacitor absorbs energy. If the power is negative, the capacitor releases energy. So in this quarter, 1 by 4th of the cycle, the capacitor absorbs energy. Again, what happens in the last 1 by 4th of the cycle? Now the current reverses this direction. It flows from B to A. When the current is flowing from B to A and the accumulated charge is depleted and the magnitude of the voltage VC is reduced. Now the capacitor is fully discharged and VC becomes 0 at 4. So now the power is negative because energy is absorbed now again. Energy is absorbed during this is returned to the source. So the net energy absorbed is 0. So that's how we talked about this already, that the power is going to be 0. The average power is 0. So in a complete cycle, when you start from 0 to pi by 2 to pi and then go to 2 pi, in a complete cycle, the average power is going to be 0. So we talked about first 1 by 4th what happens, next 1 by 4th what happens. We talked about all the 4 different quarters. Okay. Now we have come to an LCR circuit. What is an LCR circuit? In the previous circuit, we had a power source, which is alternating power source, and we had a capacitor. Now I am adding a resistor with a resistance value R. I am adding an inductor with an inductance value L. Again, we will always start with the source. What is the source voltage? V equal to Pm sin omega t, right? Now, we are going to look at each of this element. Again, let's apply Kirchhoff's rule like we did in the case of the capacitor. So, now in this case, this is the only source here. All these are drains. So, the overall sum of all the voltage drops is going to be 0. So, the source voltage V should be equal to the voltage drop across the R, which is nothing but I into R. This comes from Ohm's law. And what is the voltage drop across the capacitor? Q by C. What is the voltage drop across the inductor? Which is L into di by dt. So all of this, summing up all the voltage drops across these three elements, have to be equal to the source voltage. So this is the starting point where we are going to start the analysis. So we want to determine the instantaneous current. So current at a particular time and its phase relationship with the applied alternating voltage, just like we did in the previous cases. So here is a phasor diagram. Look at it. So I is directly in the same place where there is a VR. So what is VR? That is the voltage across the resistor. This is voltage across the inductor. This is voltage across the capacitor. Right? I is the current. So from the circuit shown, we see that the resistor, inductor and capacitor are in series. Whenever the elements are in series, they can have only one current flowing through all of them. So what is that current that is flowing through all of them? I equal to Im sin omega t plus phi. In the capacitor case, we had instead of a phi here, we had a pi by 2. But in this case, we don't know what is the angle. So we are going to say phi. Phi is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learned in the previous sections, we should construct the phasor diagram for the present case. So how are we constructing? Let's look at the resistor first. We know the voltage across the resistor and the current are going to be in phase because resistor does not contribute to any kind of phase difference. When you have a resistor in a circuit, it does not contribute to any kind of phase difference, so it's going to be the same. But we know for a capacitor, the current always leads pi by 2 degree. So that's why the capacitor voltage is here, but the current is 90 degrees ahead of this. But for an inductor voltage across the inductor, the current is going to be lagging for pi by 2. So this is the circuit, this is the phasor diagram. Now let's look at the calculations. Now I want to find out what is the overall voltage. Okay, so if I want to find out what is the overall voltage, how do I do that? So yeah, what is I here? I is equal to Im sin omega t plus phi, and we already looked at what is VL, VR, and VC, and overall V. V represents the final magnitude, or that is the resultant of all these three categories. How do we find the resultant of all these three? First, let's look at VL and VC. If I want to find the resultant of these two vectors, how do I do that? I want VC added with VL, but VL is in the opposite direction. So it will become VC minus VL. So what is VC minus VL? That is this vector. So what is the magnitude of this vector? Amplitude of VCM, that's nothing but amplitude of VC and amplitude of VL. This minus this will give me this distance. And if I want to find out what is the resultant, complete resultant, I have to add this element with the element across the resistor VR. So the overall resultant is going to be this V here, which has a magnitude of Vm. So from the previous section, we know that VR is parallel to I, VC is pi by 2 behind I, and VL is pi by 2 ahead of I. So after taking care of all of this, then we have the resultant is equal to V, and we know VRM, that magnitude of VR is going to be IMR and magnitude of VC is going to be IM into XC. Similarly, magnitude of VL is going to be, or amplitude of VL is going to be Im multiplied by XL. So the phasor relation whose vertical component gives the above equation is the result. The resultant is going to be VL plus VR plus VC. So since they are all vectors, we find the resultant in this way. Okay. So V is represented as hypotenuse of the right angle triangle whose sides are VR and VC plus VL. The Pythagorean theorem gives you Vm squared equal to Vrm squared plus Vcm minus Vlm the whole square. This right angle triangle here, if you take this hypotenuse is the resultant capital V, which has an amplitude of magnitude of Vm. So from the Pythagoras theorem, you can write like Vm square equal to Vrm square plus this whole term, the whole square. So that's what we have written here. Substituting the values of Vrm, Vcm and Vlm. What is Vrm? Vrm is Im into R. Vcm is Im into Xc. Similarly, Vlm is Im into XL, the whole square. So if you substitute all these values, then you get this equation. So take Im square outside, then you get R squared plus Xc minus XL the whole square. So again, Xc is capacitive reactance, XL is inductive reactance. So you get Vm equal to this. So what do you do for Im? Just rearrange this equation and take the square root on both sides. Then you get Im equal to Vm divided by square root of R squared plus Xc minus XL the whole square. Now if you look at this equation, it again resembles Ohm's law. So how does it resemble Ohm's law? I equal to V by R. Instead of R, you have this whole term which is equivalent to a resistor for the circuit. In the case of capacitor, we had 1 by omega C, if you remember, that is Xc. Now, since you have all three elements in the circuit, you have a term here which represents the factor that limits the current in the circuit. That factor is nothing but your Z. Z is nothing but impedance of the circuit. So when we say impedance, it is an equivalent resistor for a circuit which consists of a resistor, a capacitor, and an inductor. So what is the value of Z? Z equal to square root of R squared plus Xc minus XL the whole squared. Remember that this value of impedance depends on the applied frequency. How? Because Xc and XL, both of them contain the term omega. Omega has the applied frequency. So how much resistance your circuit is giving to the voltage, giving to the current, depends on what is the applied voltage's frequency also. So that's the beauty here, because since we are dealing with alternating current instead of direct current, we have to take into account the frequency of the applied voltage also. So Z, this is the final value of the Z. Okay. So we found the magnitude of the current, and now let's find out what is the phase value. So if you look at the phase phi, tan phi equal to, from the right angle triangle, because we calculated a Vm square from this equation, from this right angle triangle. So from the same triangle, if you take tan phi here, which is equal to Vcm minus Vlm divided by Vrm. So the same thing we have here, Vcm minus Vlm divided by Vrm. So if you substitute the values of Vcm, Vlm and Vrm and then cancel out all the Im values, because we know Vcm is nothing but Im multiplied by Xc, Vlm is Im multiplied by LXL, Vrm is Im multiplied by R. So if you cancel out all the Ims, you get tan phi equal to Xc minus XL divided by R. So this is a beautiful equation. What does it tell you? The phase difference phi between the current and the voltage, applied voltage, is going to be dependent on your capacitive reactance minus the inductive reactance divided by the resistance in the circuit. Look at it, the capacitive reactance gives rise to a phase difference between the current and the voltage. Similarly, the inductance also gives rise to a phase difference, but the resistance does not give rise to any kind of phase difference. So that's how all these three terms determines what will be your tan phi. Okay. So again, what is phi here? Phi is the phase difference between the voltage, the resultant voltage, and the current in the circuit. This is nothing but this phase difference. See, if you look at this maximum of voltage is here, the maximum of current is here. So what is the phase difference between those two? That is given by phi. Okay. So this is about an LCR circuit. So what did we do so far? We considered an LCR circuit and then we found out what is the solution by looking at the phasor diagrams. But now we are going to do an analytical solution. Analytical means just by mathematically working out the solution, we are going to arrive at the same conclusions. Okay. So let's look at the equation again. This is where we started. This is Kirchhoff's So now we have in the right hand side Vm sin omega t. So this is the overall equation. So whenever you want to solve a differential equation, you can assume a general solution. So I'm going to assume a solution of q equal to qm sin omega t plus theta. So now what is qm here? Qm is the magnitude or amplitude of the charge, and sine is, you know what is sine, and omega is the frequency, theta is the phase. Now if I differentiate this, then I get qm omega cos omega t plus theta, and differentiate it again, you get minus qm omega squared sin omega t plus theta. Now what do? We assumed a solution. Now we are going to substitute the solution into this equation and see what happens. So let's substitute L d squared by q by dt squared. Instead of d squared q by dt squared, you substitute this whole term. Similarly, you substitute all these terms and then rearrange the terms, then you get this equation. So this is the term that contains R here. So this is the term that contains L and C. If you rearrange and then substitute 1 by omega C equal to XC and omega L equal to XL, then you get this equation. Okay. Now we know that Z equal to square root of R squared into R squared plus XC minus XL the whole square. Now in the left hand side of this equation, let's multiply and divide it by Z. So you have Qm omega Z multiplied by R by Z cos omega t plus theta plus XC minus XL divided by Z into sin omega t plus theta equal to, the right hand side remains the same from beginning, which is nothing but the applied voltage Vm sin omega t. Now R by Z equal to cos phi. Why is it so? Because of the right angle triangle, which we talked about already. Phi is nothing but the angle, and this is just opposite side by adjacent side, opposite side by hypotenuse. Okay. So then you get, what is sin phi then? Xc minus XL by Z. We know that cos phi is R by Z and sin phi is Xc minus XL by Z. So we can substitute these values here. And we already know what is, okay, if you have cos phi and sin phi, you can easily find out what is tan phi. And so what is phi? Phi equal to tan inverse of Xc minus XL divided by R. Substituting this in equation 7.31 and simplifying, 7.31 is the original equation which we started with, and then simplifying, then we get qm omega z cos omega t plus theta minus phi equal to Vm sin omega t. Comparing the two sides of this equation, if you look at these two sides of this equation, this qm omega z contributes to Vm, and the sin omega t should be equal to cos omega t plus theta minus phi. So then this theta minus phi should be equal to minus phi by 2, because that is the relationship between cos and sin. So then what is the value of theta? Theta should be minus pi by 2 plus phi. So substitute all of this here. So we have Im, that is the magnitude of the current or the amplitude of the current, equal to Qm omega Z, and substituting this here, I equal to dq by dt, which is equal to Qm omega cos omega t plus theta. So Qm and omega, we can say that it is equal to Im. So I equal to Im sin omega t plus phi. So now we can find out what is the magnitude of Im. Im equal to Vm divided by Z. And what is Z? Z is nothing but square root of R squared plus Xc minus XL the whole squared. And we know what is the phi value. So what did we do here is, we found out what is the value of Im and what is the value of phi by just doing the analytical method. Okay, now we are going to talk about a concept called resonance. Resonance we already studied in other classes. In mechanics, we know what is a resonance. So every system has a natural frequency. When applied frequency matches with the natural frequency of the system, then the amplitude of oscillation is going to be really high. Then we call this as resonance. So an interesting characteristic of the series RLC circuit is the phenomenon of resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. So this frequency is what we call as natural frequency. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be very large. So a familiar example is a child on a swing. The swing itself has a natural frequency, and the swinging will be back and forth, and the magnitude will be really high if the applied force also matches the same frequency. Similarly, these RLC circuits have many applications, like filter circuits, oscillators, voltage multipliers and all. Why do we have them? Because we can select a particular frequency when you are tuning a radio or a TV system, because this RLC circuit has a particular resonance frequency. If that frequency matches with what frequency you're receiving, then the amplitude will be high. So then the signal will be really high. This is how the tuning of radio and TV system works. So what is resonance frequency? Let's look at that. So we know the equation of current Im equal to Vm by Z, which is equal to Vm divided by square root of R squared plus Xe minus XL the whole squared. Now, when will this term be maximum? So for this term to be maximum, the denominator has to be minimum. But R, we cannot do anything. R squared will always be positive. We can't do anything. But this term can become 0. When will this term become 0? When Xc becomes equal to XL. So Xc is 1 by omega C, XL is omega L. When these two terms are equal at a particular frequency omega 0, then what happens? This term here in the denominator becomes Z equal to square root of R squared plus 0 squared, which is equal to R. So now Xc becomes equal to XL and 1 by omega 0 C equal to omega 0 into L. Then omega 0 is equal to, when you rearrange these terms, then you get 1 by root of LC. So this is your resonance frequency. Why do we call this as resonance frequency? This is the frequency that gives rise to the minimum of the Z value. When the Z value is minimum, that means the current will be maximum. So if you look at this equation, for different omega values, the value of current is also different. But at a particular frequency, the current attains a maximum value. That frequency is called the resonance frequency, which is given by 1 by root of LC. It's so beautiful here. You can actually design your circuit based on what frequency of the signal you want to pick up. So that's how when you tune the radio, you're actually changing the values of L and C in the circuit so that you pick up a particular frequency. So this particular frequency of oscillation of an LCR circuit can be designed based on these values, right? Can be chosen based on these values. Okay, what is the sharpness of resonance? When there is a peak where the resonance occurs here, sharpness means how sharp is this peak. So that's what we are going to study. Okay, so the amplitude of current in LCR circuit is given by this, which we already studied. And if you substitute XL equal to omega L and X equal to 1 by omega C, the equation becomes like this. And we know what is omega 0, the natural frequency, is equal to 1 by root LC. So at this particular frequency, the current value becomes maximum. What is the maximum current value? It will become Vm divided by R, because this term becomes 0. So this is the maximum current value, which is Vm by R. Now, from the above resonance curve, it is found that the curve is symmetrical at omega equal to omega 1 and omega equal to omega 2. So at omega 1 equal to omega 0 plus delta omega. So we are choosing a frequency which is on the right side of omega 0, which has a value of delta omega away from omega 0. This is at the left side of omega 0 at a value of delta omega below the omega 0. Okay, at these two frequencies, the value of current has to be same. So what is the bandwidth of the circuit? It is nothing but the difference between these two, so which is nothing but 2 into delta omega. So if you divide the natural frequency or the resonance frequency by the bandwidth, then you get the sharpness of resonance. So how do we get the sharpness of resonance? It is omega 0 divided by 2 delta omega. 2 delta omega is the bandwidth and omega 0 is the resonance frequency. So naturally, if this term omega, delta omega becomes smaller and smaller, the peak becomes sharper and sharper. That's how we get the sharpness of the resonance. Suppose we choose a value of omega for which the current amplitude is 1 by root 2 times the maximum value. So the power dissipated by the circuit becomes half. Why the power becomes half? Because 1 by root 2 multiplied by Vm and 1 by root 2 multiplied by Im becomes 1 by 2 multiplied by Im into Vm. So the power will be half of its maximum value. So let's look at this at some particular frequency at omega 1. The current value is 1 by root 2 of the maximum value. 1 by root 2 multiplied by the maximum value at this particular frequency. So let's match this two equations. So 1 by root 2 of I maximum equal to Vm divided by this whole term. Okay. Now we can rearrange this equation. What is I maximum? Vm by R. Okay, this is at the resonance. So it is Vm by R. Now we can cancel Vm both sides. Then you get 1 by root 2 R equal to this value. And you can just rearrange these terms. You can bring this to the right hand side. You can bring this to the left hand side. Then you get root 2 R equal to square root of R squared plus omega 1 L minus 1 by omega 1 C the whole squared. So if you take square of both sides, then you get 2r squared equal to r squared plus omega 1l minus this whole term. So r squared, if you can bring this to the left hand side, then you get r squared equal to omega 1l minus 1 by omega 1c the whole squared. So r equal to omega 1l minus 1 by omega 1c. Now what is omega 1? Omega 1 is nothing but omega 0 plus delta omega. So substitute it here, then you get omega 0 plus delta omega into L minus 1 by omega 0 plus delta omega into C equal to R. So we can substitute the value of, okay, now we are rearranging this, then you get omega 0 L plus, multiplied by 1 plus delta omega by omega 0 minus omega 0 L divided by 1 plus delta omega by omega 0 by substituting this value. So after rearranging all the terms, and then finally you will get delta omega equal to R divided by 2L. So if you rearrange this equation, then you get delta omega equal to R divided by 2L. What is delta omega? It is the sharpness of the peak, bandwidth of the peak. How broad is the peak? That is decided by the value of resistor in the circuit and the value of inductance in the circuit. Now we are going to talk about another factor called quality factor. So what's a quality factor? Quality factor is nothing but the sharpness, omega 0 divided by 2 delta omega, which is equal to omega 0 divided by, instead of delta omega, in the previous equation we found that it belongs to, it is equal to R divided by 2L. So if you substitute this and cancel out this 2 in both sides, then you get omega 0 L by R. This is called quality factor. So this decides how sharply your circuit picks up the signal. So Q equal to omega 0 L by R. We can play around with this equation a little bit more. Instead of omega 0, you can substitute 1 by root LC like this, and then you get the value Q equal to 1 by R into root LC. And you can also, from this point, you can also arrive at Q equal to 1 by omega 0 into CR. If you look at this, the quality factor depends on all three values of the components L, C and R. So the Q factor indicates the number of times the voltage across L or C is greater than the applied voltage at resonance. The selectivity or sharpness of a resonant circuit is measured by the quality factor or Q factor. So this is nothing but the sharpness factor that is measured by the quality factor. So we'll stop here. Thank you.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology, for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.